For billions of years, one ancient landmass lay erased from popular history, Columbia, also known as Nuna, a forgotten supercontinent that formed long before Pangaea or even Rodinia. In Earth's deep childhood, its fused continents guided ocean currents, built mountain chains, and helped shape the planet we know today. In this video, we uncover how scientists reconstructed this lost world and why it matters. If you enjoy journeys into deep time, please like, subscribe and share, and tell us in the comments what surprises you most about a supercontinent that existed before all others. Thank you for watching. Now let's begin. Early in the Proterozoic Eon, about 2,200,000,000 to 2,100,000,000 years ago, Earth is a restless planet. A global ocean covers most of the surface, dark and deep, interrupted by scattered areas of land. These lands are groups of thick ancient crust that geologists later call cratons. A craton is a stable block of continental crust that has survived many earlier collisions and rifting events. Each craton now stands as a patch of buoyant rock rising above the denser oceanic crust around it. The shapes of these blocks are irregular. Some are broad central masses with attached fragments at their edges. Some are smaller and more isolated, separated from their neighbours by wide ocean basins. There is no single continuous landmass that wraps far around the globe. Instead, continents exist as clusters and chains of high-standing crust surrounded on all sides by ocean waters. The interior of the planet is hotter than in later times. Heat left over from Earth's formation is still being lost, and heat from the decay of radioactive elements is stronger than it will be billions of years later. This excess heat keeps the mantle, which is the rocky layer between the core and the crust, in a state that convects vigorously. Mantle convection is the slow plastic flow of hot rock, rising and cooler rock sinking over very long timescales. This movement sets the plates at the surface in motion. The rigid plates include both oceanic crust and continental crust. They slide past one another, move apart, and collide along long shifting boundaries. At this time, plate boundaries may be more numerous and may change more quickly than in later eras, because the hotter mantle can drive more rapid change in plate positions. Where plates move apart, new oceanic crust forms along mid-ocean ridges. These ridges are long raised zones where mantle material rises, melts and solidifies to build fresh basaltic crust. The ocean floor near these ridges is young, warm and relatively high. As it moves away from the ridge, it cools, becomes denser and sinks deeper into the mantle, carrying the seafloor with it. Where plates converge, one plate often bends and sinks back into the mantle along a subduction zone. A subduction zone is a long, narrow region where oceanic crust descends beneath another plate. Above the descending slab, water and other materials drive melting in the mantle, and magma rises to feed chains of volcanoes. In many places around the early Proterozoic globe, such subduction zones run roughly parallel to the margins of the ancient continents, tracing arcs of volcanoes and growing mountain belts. The scattered cratons have different histories but share some common features. Their inner regions are made of very old rocks that formed in the Archean Eon and earlier Proterozoic times. These rocks include granites, gneisses, and greenstone belts, which are bands of volcanic and sedimentary rocks that have been deformed and metamorphosed. Around the cores of the cratons lie younger belts of deformed rocks, where older continental fragments and island arcs have collided and welded together. These belts record earlier stages of continental growth in which smaller pieces joined to form larger, more coherent blocks. In the early Proterozoic setting described here, these belts are already in place. They form stiff spines within each continent, giving the cratons mechanical strength and allowing them to act as single units as the plates move. The ocean that surrounds the scattered continents is broad enough to encircle the planet. It does not yet have the pattern of distinct major ocean basins and narrow seaways seen in much younger times. Instead, there is one vast connected body of water with regional differences in depth, temperature and chemistry. In some regions near active plate boundaries, volcanic islands and growing arcs break the surface and dot the ocean. In other regions, long passive margins stretch away from the cratons with thick piles of sediments slowly building out into the sea. A passive margin is a continental edge where there is no active subduction or collision. At these quieter edges, erosion of the continents supplies sand, mud and dissolved ions that rivers deliver to the sea. Over long spans of time, these materials settle and accumulate, forming broad wedges of sediment that gently thin away from the land. The atmosphere at this time holds more oxygen than in Archean times, but it is still lower than in later eras. Earlier, a major shift in atmospheric chemistry, often called the Great Oxidation Event, raised oxygen from extremely low levels to a more noticeable but still modest fraction of the air. In the early Proterozoic world described here, that transition lies in the geologic past, but its effects continue. Iron in seawater now tends to oxidize and precipitate more readily, changing the way sediments form on the ocean floor. On land and in shallow seas, weathering reactions are influenced by the presence of free oxygen. However, the atmosphere remains different from that of the present. Greenhouse gases such as carbon dioxide are likely higher than in later times, helping to keep global temperatures above freezing, even though the sun is somewhat fainter than today. At the surface, climates vary from region to region, but there is no single clear pattern of very long global scale ice cover in this specific interval. Much of the rock record from this part of the Proterozoic suggests moderate conditions in many regions. Warm, shallow seas spread over some continental margins, while other edges are more storm-dominated with strong waves, and currents reworking sediments along broad continental shelves. Inland from the coast's low to moderate relief landscapes dominate many continental interiors. Weathering slowly breaks down exposed rocks. Rivers carry the resulting sediments from high-standing areas toward basins at lower elevations. Over very long timescales, this combination of erosion and deposition tends to smooth out topography, leaving old mountain belts as subdued uplands, and filling intervening basins with thick sedimentary sequences. The biosphere at this time is dominated by simple life. Microbial communities thrive in the oceans on continental shelves, and in some surface environments on land. In shallow marine settings, mats of photosynthetic microbes build layered structures known as stromatolites. A stromatolite is a laminated rock created as microbial mats trap and bind sediment, and as minerals precipitate around them. These structures grow slowly, layer by layer, and can persist for long periods in environments where grazing and burrowing organisms are scarce. In deeper waters, other microbial communities carry out different metabolic processes, contributing to the cycling of carbon, sulfur, and other elements. Life is already an important part of Earth's surface systems, but it remains microscopic and relatively simple in form. Beneath the surface, the thick cratonic roots extend deep into the mantle. These roots are regions of cool, rigid lithospheric mantle attached to the overlying crust. Because they are colder and thicker than surrounding mantle, they help the cratons float high and remain stable over very long times. The contrast between these thick, buoyant roots and the hotter, more deformable mantle farther away influences how mantle convection patterns develop. Hotter upwelling regions and cooler downwelling zones tend to form around the edges of these stable areas. This pattern affects where new plate boundaries form, where subduction is likely to occur, and how plates are pulled or pushed relative to one another at the surface. On the scale of the entire planet, the early Proterozoic Earth in this interval is a system in which heat loss mantle convection, plate motions and surface processes interact in a steady but dynamic way. Continental crust is concentrated into a number of large cratons and attached fragments, each with a long earlier history already recorded in its rocks. Wide oceans separate these blocks, but also link them through circulation of water heat and dissolved substances. Subduction zones, mid-ocean ridges transform faults, and other plate boundaries set the pattern of relative motion among plates, and thus determine how continents approach or move away from each other. Over tens of millions of years, the changing balance of forces at these boundaries, together with the structure of the mantle and the geometry of existing continents, controls the long-term paths that the scattered continental blocks follow across the surface of the globe. In this early Proterozoic world, the large areas of land are not yet a single joined mass, but exist as separate stable blocks with their own long internal histories. Each block is a craton, a thick piece of continental crust with a deep, cool root in the mantle, and together these blocks form the main areas of dry land that rise above the global ocean. Some of these cratons later carry the names Laurentia Baltica, Siberia, North China, South China, India, Australia, Amazonia, the West African Craton, the Congo Craton, and the San Francisco Craton. At this time they stand apart from one another. Wide ocean basins, volcanic island arcs, and smaller fragments lie between them. The exposed rocks within the inner parts of these cratons are mostly very old. Many formed in the Archean Aeon more than 2,500,000,000 years ago, and some are even older. They include banded gneisses, ancient granites, and remnants of old volcanic and sedimentary belts. These rocks have been heated, deformed, and changed many times. In many places they are cut by younger granitic bodies that formed when partial melting took place deep in the crust. Around the oldest central cores of many cratons, belts of younger early Proterozoic rocks wrap partway around the margins. These belts are collision belts, also called orogenic belts, in which earlier continents or island arcs met and joined. The rocks in such belts show strong folding, thrust faulting, and regional metamorphism. They include long layers of deformed sedimentary rocks, volcanic rocks, that have been metamorphosed, and large granitoid bodies that intruded during and after collision. A collision belt usually marks the site of a former ocean basin. Before collision, subduction operated along one or both plate margins, carrying oceanic crust down into the mantle. As the gap between the approaching continents closed, the remaining seafloor and island arcs were squeezed, thickened, and forced upward, forming high mountain ranges. Over hundreds of millions of years, erosion removed much of the height of these mountains, leaving deep crustal levels now exposed at the surface as complexly deformed rocks. Many such belts now preserved in the shields of present continents record collisions that took place hundreds of millions of years before the time interval being described here. They show that large-scale continental assembly had already occurred more than once in Earth's history before this stage. Geologists have proposed that still earlier, supercontinents such as Valbara and Kenorland may have existed in the Archean and earliest Proterozoic. Valbara is often described as a possible link between the Karpval Craton in southern Africa and the Pilbara Craton in Western Australia. Kenorland is a name given to a proposed larger early Proterozoic landmass that may have joined several Archean blocks, including parts of what later become Laurentia and Baltica. However, the evidence for these very early supercontinents is limited and complex. The rocks involved are extremely old and have been strongly reworked by later events. Paleomagnetic signals are often overprinted or poorly preserved, and many key regions have sparse exposure or have not yet been studied in fine detail. As a result, the number, exact shapes and lifespans of these earliest proposed supercontinents remain uncertain. They show that continental crust can come together on a large scale, long before this early Proterozoic stage. By the early Proterozoic time described in this section, many of the old collision belts that may once have been part of such early large assemblies are now internal features of the cratons or lie at their edges. In Laurentia, for example, Archean cratonic blocks in what is now central Canada are linked by older Proterozoic belts. in the Fennoscandian Shield, which becomes part of Baltica Archean nuclei, are bordered by early Proterozoic belts that show long histories of subduction and collision. In parts of what is now Australia Archean and early Proterozoic blocks, are stitched together by complex origins that record repeated plate interactions. Each of these regions preserves its own pattern of belts and blocks, but all show that the land now standing as separate continents has already passed through several cycles of fragmentation and collision. The present arrangement in this interval is thus one of separate stable blocks bounded and cross-cut by belts that formed during earlier mountain-building episodes. The widths of the oceans between the cratons vary. Some pairs of cratons are separated by only a few hundred kilometers of oceanic crust, which can be consumed relatively quickly at active subduction zones. Others are divided by much wider tracts of seafloor, where oceanic plates are older, thicker, and colder. In some places, long island arcs face the margins of the cratons. In other places, smaller continental fragments ride on their own plates between the main blocks. These smaller pieces are sometimes called microcontinents. Over long time scales, microcontinents can be captured and added to the edges of larger cratons, further increasing their size. The orientation and location of these cratons around the globe are not simple to reconstruct in detail. Paleomagnetic data from rocks of this age give partial information about the latitude at which a rock formed and the direction of the magnetic field at that time. This helps geologists estimate whether a given craton lay at high or low latitude and how it rotated over time. However, many cratons have gaps in their paleomagnetic records, and some results are uncertain or have more than one valid interpretation. As a result, maps of early Proterozoic Earth use cautious lines and broad swathes to show possible positions and shapes rather than precise outlines. What is clear is that the cratons are not clustered into one dominant supercontinent in this interval. Instead, they form several groups and chains separated by oceans of different widths. Collision belts connect some blocks into longer trains, while others stand more isolated with only narrow shelves and small surrounding fragments. The pattern of cratons and collision belts at this time sets the mechanical structure of the continents. Old strong cratonic cores resist deformation. Younger belts at their margins are more easily reactivated when new forces act on the plates. Where three or more belts intersect the crust may already be weakened by multiple past events. These contrasts in strength influence how plate motions in this interval distribute deformation. They help localize active subduction extension and mountain building along some belts, while other regions remain relatively stable. In this way, the arrangement of cratons and inherited collision belts defines the mechanical framework of the continents in the early Proterozoic world. As the early Proterozoic plates continue to move across the surface of Earth, patterns begin to emerge in the wide ocean spaces that lie between the scattered cratons. Old oceanic crust forms at mid-ocean ridges, cools as it drifts away and grows thicker and denser with time. Once it is old enough and heavy enough, it is more likely to sink back into the mantle when it reaches a plate boundary. Along some margins, this sinking process organizes into long continuous subduction zones that run for thousands of kilometers around the edges of the major plates. A subduction zone is a boundary where one plate bends downward and slides beneath another, carrying cold, dense lithosphere into the deeper mantle. At the surface, these zones appear as deep ocean trenches, arcs of volcanoes, and belts of earthquakes that dip from the trench toward the interior of the overriding plate. In the early Proterozoic setting considered here, many subduction zones are linked to the margins of large cratons or to chains of island arcs that stand offshore from the continents. The sinking of old seafloor at these margins exerts a steady pull on the attached plates. This pull, often called slab pull, combines with a push from mid-ocean ridges and forces applied by mantle flow to drive plates toward or away from each other. Where subduction zones face one another on opposite sides of an ocean basin, each slab pulls its own plate toward the center of the basin. Over tens to hundreds of millions of years, this can shorten the distance between facing continents. In some regions, subduction zones slowly migrate toward a continent as the downgoing plate rolls back into the mantle. As this rollback continues, the overriding plate may extend, forming back arc basins behind the volcanic arc, or may experience repeated episodes of compression as nearby blocks collide. In other places, the subducting plate steepens and the overriding plate is strongly shortened, building thick mountain belts that later erode. The specific style of each segment depends on the age of the lithosphere, the strength of the crust, the rates of plate motion, and the details of mantle flow beneath. Although these details vary from place to place, the overall pattern is that long belts of subduction and convergence are the main system that moves formerly distant cratons closer together over geological time. Around some cratons, subduction operates along almost continuous arcs for very long spans. New magmatic arcs build outward as successive pulses of magma rise from the mantle, wedge above the downgoing slab. Thick piles of volcanic rocks, intrusive granitoid bodies and related sediments accumulate. As time passes, fragments of island arcs, microcontinents and ocean floor are scraped off and welded to the edge of the main continent. This process is called accretion. The result is an accretionary margin where the continent grows outward in a series of steps. Each step adds new crust to the margin and thickens the lithosphere beneath, changing how the plate responds to later forces. In other regions, two continents lie on either side of a zone of long-lived subduction. Here the oceanic plate between them is gradually consumed. As the last fragments of oceanic crust disappear, the buoyant continental margins approach and eventually meet. When they collide, subduction of the dense oceanic plate may cease or shift to a new location, and the two continents become locked together along a collision belt. Thick crust piles up, high mountains rise, and deep roots form beneath them. Such collision belts, once the site of the final closure of ocean basins, later mark the sutures along which separate cratons have been joined. At this stage, the world map still shows many oceans and several main continents, but the distribution of subduction zones concentrates convergence in certain broad regions. Long arcs wrap around groups of cratons and smaller fragments, while other ocean domains remain more open. Geologists infer these patterns from the distribution of ancient magmatic belts, metamorphic zones, and associated sedimentary basins that formed roughly between 2 billion, 100 million, and 1 billion 800 million years ago. In present shields, these belts appear as broad zones of deformed and recrystallized rocks, such as gneisses and schists, that formed at moderate to high temperatures and pressures cut by voluminous granitoid intrusions. Radiometric dating, which measures the decay of radioactive elements in minerals, shows clusters of ages that fall in this interval, marking the time when heat and deformation were at their peak. In some cases, these belts clearly separate older cratonic nuclei with distinct earlier histories. Such relationships make it likely that they formed as true collision zones between once distant crustal blocks. In other cases, the belts reflect long-lived subduction and accretion along the margin of a single large craton where arcs, microcontinents, and thick sediment piles were successively added. In both settings, the presence of regionally continuous belts of similar age on more than one present continent suggests that the same broad system of convergent margins influence multiple parts of the globe. The positions of subduction zones also influence mantle flow. As slabs sink, they drag mantle material downward and sideways, helping to set up large-scale circulation patterns. Some models of mantle convection for this time propose that these downwelling zones lie beneath or near the edges of the major cratons, while broad upwelling regions occupy parts of the mantle beneath the large ocean basins. The contrast between cold, dense slabs and warmer, more buoyant mantle affects how plates move, how fast they travel, and where new plate boundaries form. Because the cratons have thick, strong roots, they respond to these forces largely as rigid units. Their interiors remain relatively undeformed, while most shortening and extension concentrate at their margins and along pre-existing belts. Over long intervals, this preference for reactivating older weaknesses means that younger collision belts often develop near or along the traces of older ones. Sedimentary basins also respond to the evolving pattern of convergence. In front of growing mountain belts, flexure of the lithosphere creates foreland basins, which are long downwarped regions that fill with sediments eroded from the nearby highlands. These basins record the timing and intensity of mountain building at the convergent margins. Farther out on the continental shelf, changes in sea level and crustal thickness adjust the depth of shallow seas, influencing where broad accumulations of carbonate sediment such as limestone can grow. As subduction zones migrate or shift location, some older basins are uplifted, deformed, and added to the cores of new belts, while new basins form elsewhere. All of these changes take place on timescales of tens to hundreds of millions of years, during which the positions of continents at the surface are slowly but steadily adjusted. Although the exact geometry of the early Proterozoic plates is not fully known, the geological record makes clear that this is a time when subduction and convergence operate on a large scale around many of the main cratons. The existence of widespread belts of deformed rocks and magmatic arcs of similar age on several present-day continents indicates that long-connected systems of subduction zones circle much of the globe. In such a setting, the scattered cratons and smaller fragments are not moving in a random way. Their motions are guided by the evolving pattern of convergent boundaries that encircle and partition the great ocean spaces between them. During the interval from about 2,100,000,000 to about 1,800,000,000 years ago, the pattern of subduction and convergence that has been active around the globe leads to a series of large continental collisions. Several of the main cratons move into positions where the oceans between them narrow, their facing margins approach, and eventually their buoyant continental crust makes contact. When this happens, the style of deformation changes from smooth subduction of dense oceanic plates to a complex zone where two thick continental blocks collide. The crust in the collision zone shortens, thickens, and heats up. Rocks that once lie near the surface are carried to greater depths where they are strongly deformed and metamorphosed, then later uplifted again. The result is a broad belt of deformed rocks that geologists call an orogen or mountain belt. Such belts form the main record of large-scale collisions in this time window and mark the places where separate cratons become joined. A key region in this process is the area that later becomes the central part of Laurentia. Older Archean blocks here, including provinces in what is now central and northern Canada, are separated by oceans and younger earlier belts. As time passes, convergence brings these blocks together. Long orogenic zones grow between them as intervening oceanic crust is subducted and finally consumed. One of the largest of these belts, known in modern terms as the Trans-Hudson Orogen, links several Archean provinces into a single continuous continental mass. Similar belts of comparable age form along the southern and western margins, recording further collisions and accretion of smaller fragments. Each belt has its own detailed sequence of volcanic activity, sedimentation, deformation, and metamorphism, but together they show that this region passes from a state of separate blocks and basins to a joined continent with extensive regions of ancient crust. These collisions are not limited to the region of Laurentia. Other cratons also converge and meet during this time. Parts of what later become Baltica, Siberia, and Amazonia experience major episodes of mountain building and crustal growth between about 2 billion and 1,800,000,000 years ago. In present-day shields, these events are preserved as wide zones of high-grade metamorphic rocks, large granitoid intrusions, and deformed sedimentary and volcanic sequences. Radiometric ages from minerals such as zircon cluster in this time range, indicating widespread heating and partial melting of the crust. In several regions, the age patterns, rock types, and structural trends suggest that once separate cratonic blocks are brought together and welded along collision zones. When geologists try to place these belts into a global context, they find that many continents preserve origins of similar age and style. This repeated pattern is one of the main reasons to infer that a supercontinent forms during this time. The exact positions and orientations of the cratons within that supercontinent are still a matter of study. Paleomagnetic data constrain latitudes and some aspects of rotation, but do not on their own fix east-west positions. As a result, several different reconstructions exist for how Laurentia, Baltica, Siberia, Amazonia, and other cratons are arranged. Some models place Laurentia near the center with Baltica and Siberia attached along long sutures on one side and Amazonia along another. Other models adjust the relative positions or emphasize different collision belts as the main joining zones. Despite these differences, most reconstructions agree that by about 1,800,000,000 years ago, many of the major cratons are linked into a single large landmass that geologists call Columbia or Nuna. Within the growing landmass, the collision belts act as sutures. A suture is a zone where an ocean basin closes and two continents or continental fragments become attached. In some sutures, remnants of former oceanic crusts such as slices of basalt and ultramafic rocks are preserved and later exposed. In others, the oceanic crust is completely subducted, and only the deformed sediments and magmatic rocks of the convergent margins remain. The crust along these sutures is often thicker than in surrounding regions because of intense shortening and addition of magmatic material. Deep underplating of magma and repeated deformation can build roots that extend far into the mantle. Over time, as mountains erode, these deep levels are exhumed and now form wide tracts of high-grade metamorphic rocks in present-day shields. The process of building Columbia's core is not a single brief event, but a sequence of collisions and accretion episodes spread over tens to hundreds of millions of years. As one pair of cratons collides and sutures other nearby oceans continue to narrow. Island arcs and microcontinents move along complex paths, sometimes colliding first with one large block and then with another. Each event leaves its mark as another belt of deformed and magmatic rocks. The overall pattern is one of stepwise growth in which the area of joined continental crust increases as more blocks become attached. By the later part of this interval, the number of wide, long-lived ocean basins between the major cratons has decreased. Instead of several separate continents surrounded by oceans on all sides, there is now at least one region where many cratons are directly connected by collision belts. Above this, joined core mountain ranges stand high, although the exact shapes and elevations are not known in detail. Erosion wears down exposed peaks, carrying sediments into fallen basins and nearby shallow seas. These sediments, composed of sand, silt, and clay, build thick wedges along the flanks of the new mountain belts. As they are buried, they compact and lithify into sedimentary rocks. Some of these rocks are later deformed and metamorphosed during younger events, but others survive with relatively modest deformation and give a record of erosion and basin filling during and after collision. The distribution of such basins helps show where long continuous mountain belts once stand along the sutures. At the same time, magmatic activity remains strong in many parts of the growing supercontinent core. Partial melting of thickened crust and of the underlying mantle produces large volumes of magma that rise and solidify as granitic and related intrusive bodies. Some reach the surface and feed volcanoes, while others cool slowly at depth. These granitic bodies contribute to the buoyancy of the continental crust, because they are less dense than many of the rocks they intrude. Their presence also helps bind together different crustal slices by forming wide regions of relatively uniform material. Over long periods, this magmatism contributes to the stabilization of the newly formed continental core. Although the main theme of this time is collision and assembly, not all margins of the growing landmass are the same. Some edges remain active convergent plate boundaries where subduction continues, and new arcs and accretionary complexes build outboard of the main sutures. Other edges are calmer with more passive style sedimentation along broad continental shelves. In this way, the emerging Columbia has a complex perimeter marked by a mix of active and quiet margins. The pattern of these margins and which craton sits next to which still carries uncertainties in current reconstructions. However, the presence of many belts of similar age and style across widely separated modern continents supports the idea that an extensive region of joined continental crust exists at this time. By the close of this interval, Earth displays a large joined region of thick continental crust surrounded by a global ocean. The lands that once stand far apart have, through the slow but persistent action of plate motions, subduction, and collision, become connected into a continuous interior. The details of its outline and the exact arrangement of each craton are not fully resolved, but the geological record gives a consistent picture of a major step in continental assembly. This joined region forms what geologists describe as Columbia, or Nuna, a Paleoproterozoic supercontinent that now occupies a significant fraction of Earth's surface as a single continuous landmass. During the time after about 1,800,000,000 years ago, the main collisions that build the core of Columbia have already taken place. The thick blocks of continental crust that once stand apart are now linked by broad belts of deformed and metamorphosed rocks. These belts mark the sutures where former oceans have closed. Along them, the crust has been shortened, heated, and intruded by large bodies of magma that solidify as granitic rocks. The result is a single continuous landmass that reaches across a large part of Earth's surface. Its exact outline remains uncertain in modern reconstructions, but geological evidence shows that many of the major cratons are now joined into one dominant supercontinent. Around this joined landmass lies a wide encircling ocean. This exterior ocean is the main reservoir of surface water on the planet. It stretches away from the continental edges for thousands of kilometers before any other large land appears. Small island arcs, microcontinents, and submarine plateaus rise from its floor, but there is no second continent of comparable size standing opposite Columbia. The contrast between thick, buoyant continental crust in the supercontinent and thinner, denser oceanic crust in the surrounding basin gives Earth a clear separation into one major landmass and one broad superocean. The sutures inside Columbia do not remain zones of intense deformation forever. Once the main collisions have finished and plate convergence slows or shifts elsewhere, the crust along these belts begins to cool and strengthen. The high mountain ranges that once stand above them are slowly worn down by weathering and erosion. Rain rivers and moving ice in cooler regions break rock apart and carry fragments downslope. Over millions of years, this process removes large volumes of material from the mountain belts and deposits it in nearby basins and along the continental margins. As erosion cuts into the thickened crust, deep levels that form during collision are gradually brought closer to the surface. Rocks that once lie at depths, where high temperatures and pressures transform their minerals, now appear in large exposures in the core of the supercontinent. These exposures include gneisses and schists that record intense deformation, as well as migmatites, which are rocks that partially melted during peak metamorphism. They preserve evidence of the conditions that exist when the sutures are active. Farther away from the central parts of the belts, less deformed sedimentary rocks fill fallen basins that formed in front of the growing mountains. These rocks document the history of erosion and basin filling as the ranges rise and then decay. Together, these features show that the sutures are no longer places where new major deformation is focused, but they remain clear structural and compositional boundaries within the continental interior. As the interior belts cool, the thermal state of the entire supercontinent adjusts. Thick crust and deep lithospheric roots act as an insulating lid over the underlying mantle. Heat from below tends to accumulate beneath the continent, while heat produced within the crust by radioactive decay also contributes to warming the lower levels. Over long timescales, this can drive changes in the pattern of mantle flow. Some models suggest that warm mantle may slowly rise beneath the central parts of the continent, while cooler material sinks around its edges. Although the precise flow patterns are uncertain, it is clear that the presence of a single large block of thick lithosphere affects how heat is transported from the interior of the planet to the surface. At the same time, the surface of Columbia becomes more unified in its large-scale structure. Old cratonic cores that were once separated by oceans are now simply different regions within the same continuous landmass. Their boundaries are marked by the old sutures, but there is no longer ocean water between them. Instead, there may be long inland basins, broad plateaus, and low ranges that follow the traces of the former collision belts. Sediments derived from erosion of the old mountains spread across adjacent regions, blanketing parts of the cratons and filling depressions. Over very long periods, this redistribution of material tends to smooth out topographic contrasts, although local differences in rock type and crustal strength maintain variations in elevation. The exterior ocean that surrounds Columbia responds to the new arrangement of land. The supercontinent presents a broad obstacle to ocean currents and atmospheric flow. Winds blow across wide stretches of open water before reaching land, picking up moisture and heat. When they encounter the continental margins, they drop rain that feeds large river systems, draining the interior. These rivers carve valleys into the landmass and build large deltas and coastal plains at its edges. On the submerged continental shelves that ring parts of Columbia, layers of sediment accumulate, forming extensive sequences of sandstone, mudstone, and carbonate rocks. In areas where the water is clear and shallow, carbonate platforms may grow built by chemical precipitation and by microbial communities living on the seafloor. Farther offshore, the ocean floor continues to form and subduct along ridges and trenches, but the main sense of the surface pattern is that one supercontinent stands within one superocean. The rates of plate motion and the exact positions of ridges and trenches during this time are not known in fine detail, but the net effect is that the exterior ocean basin remains open while most major land fragments are gathered into Columbia. The existence of this configuration is supported by the distribution of magmatic belts, metamorphic ages and sedimentary basins of similar age on many present-day continents. These separate records, when placed side by side, outline a time when distant cratons in their earlier state now share linked tectonic histories across what must have been a continuous landmass. In the deeper parts of the crust beneath Columbia, the switch from intense collision to a more stable, joined state allows the rocks to relax. Stresses that once drive large-scale folding and faulting diminish. New deformation becomes more localized, often reusing older structures rather than creating entirely new belts. This progressive shift in behavior marks the transition from an active assembly phase dominated by the closing of major oceans and the joining of continents to a long interval in which the supercontinent exists as a coherent unit. The world now has a single dominant aggregation of continental crust surrounded by a broad ocean basin, and the thick interior belts of Columbia have begun to cool, erode and stabilize after the earlier, more violent episodes of mountain building. During the long interval after the core of Columbia has been assembled, many of the most active parts of the supercontinent are no longer in its interior but along its edges. Around much of the perimeter of the joined landmass, wide tracts of oceanic crust continue to sink beneath the continental margins along subduction zones that have already been active for a long time. These margins form an irregular ring around Columbia, broken in places by transforms and by stretches of more passive shelf, but overall they mark a continuous system where the supercontinent meets the surrounding superocean. At the surface, these zones appear as deep marine trenches, offshore arcs of volcanoes further inboard, and belts of deformation that run parallel to the coastlines. The oceanic plates that reach these trenches are mainly old and thick. As they sink, they carry cold, dense lithosphere into the mantle. Water and other components released from the descending slabs rise into the overlying mantle wedge and promote melting. Magma generated in this way ascends feeding chains of volcanoes that sit on or near the continental margin. Over time, repeated eruptions and intrusions build thick piles of volcanic rocks and large volumes of intrusive granitoid bodies along the edges of the continent. These magmatic belts are not isolated points, but long zones that can stretch for thousands of kilometers. They record the steady, long-lived operation of subduction around much of Columbia's rim. Sediment derived from erosion of the volcanic arcs and the higher parts of the supercontinent is carried toward the margins by rivers and gravity-driven flows. Closer to the trench, some of this material is scraped off the downgoing plate and added to the edge of the overriding plate, forming an accretionary prism. An accretionary prism is a wedge of deformed sediments and ocean floor rocks that grows outward from the continent as more material is off-scraped and stacked. Farther inboard basins form in front of rising mountain belts, where the lithosphere flexes under the weight of accumulating crust. These foreland basins fill with thick sequences of sandstone, mudstone, and other sediments that record the ongoing uplift and erosion of the margin. Together, magmatic arcs, accretionary prisms, and foreland basins create wide belts of complex geology along the edges of the supercontinent. In some sectors, island arcs that once stand offshore are carried into the subduction zone and collide with the continental margin. When this happens, the island arc can be welded onto the supercontinent, bringing in new volcanic and plutonic rocks, and sometimes fragments of older oceanic crust and deep-sea sediments. This process of adding small crustal pieces to the edge of a larger continent is a common way for Columbia to grow laterally. Each accreted fragment becomes part of the permanent record of the supercontinent's margins. Over very long timescales, repeated episodes of arc collision and accretion build broad composite belts made from many such fragments. Along other parts of the margin, microcontinents or small continental blocks ride on subducting plates and collide with Columbia. Because these blocks are buoyant, they do not sink easily into the mantle. Instead, they jam the subduction zone, change the geometry of convergence, and are incorporated into the outer parts of the supercontinent. Their arrival can shift subduction to a new trench farther offshore, or along strike, leaving behind a complex arrangement of sutures, magmatic belts, and deformed sedimentary piles. These steps further complicate the structure of the margin, but also add to the area of continental crust attached to Columbia. The distribution of these long-lived active margins is not identical around the entire supercontinent. In some regions, subduction is nearly continuous along a great arc, and magmatism and deformation persist with only short pauses. In other regions, segments of subduction are separated by transform boundaries or by stretches of more passive margin where tectonic activity is lower and sedimentation is the dominant process. Changes in plate motions can switch an area from one style to the other over time. However, when geologists look at the rock record that later forms in many present-day shields, they see extensive belts of calc-alkaline magmatic rocks, high-grade metamorphic zones, and deformed sediments of Middle Proterozoic age. These features point to a time when arc accretionary complexes and long active margins are widespread along Columbia's edges. Deep in the crust beneath these margins, the ongoing addition of magma and the thickening caused by convergence together build a strong, buoyant lithosphere. Large batholithic complexes, which are huge composite intrusive bodies, made of many individual magma pulses stitched together older crustal blocks and younger accreted material. As these deep intrusions cool and crystallize, they release heat into the surrounding rocks, driving metamorphism across broad regions. The combination of magmatic addition, crustal shortening and metamorphism produces belts with a complicated internal structure, but the overall effect is to stabilize and thicken the outer parts of the supercontinent while still allowing them to be sites of continuing growth. The thermal and mechanical state of these margins influences how the mantle beneath Columbia behaves. Where slabs sink steeply, they can drag cold material deep into the mantle, enhancing downwelling there. Where they are shallower, they may interact more with the base of the lithosphere over a wide region. In either case, the presence of long subduction zones around much of the supercontinent helps organize the large-scale circulation of the mantle. Upwelling regions may develop beneath parts of the superocean, or near gaps in the ring of subduction, while downwelling dominates beneath the active margins. These patterns in turn affect the stresses experienced by the lithosphere at the edges of Columbia, shaping where deformation concentrates and how far inland it extends. Despite this complex behavior, the principal contrast remains clear when compared with the interior of the supercontinent. Inside Columbia, away from the margins, deformation is relatively limited, and many regions experience long periods of tectonic calm. Along the edges, in contrast, convergence, magmatism and mountain building continue over hundreds of millions of years. This difference marks the outer rim as a zone where much of the ongoing tectonic and magmatic energy of Earth's lithosphere is focused during this stage in the life of the supercontinent. Over time, the record of these long-lived subduction margins becomes one of the main sets of clues from which the presence and shape of Columbia are later inferred, preserved today as wide belts of deformed and igneous rocks on several modern continents. During a long interval of the Middle Proterozoic, roughly between about 1,800,000,000 and 1,500,000,000 years ago, Columbia exists as a largely joined and relatively stable landmass. The main sutures that joined its cratons have cooled and strengthened, and the broad belts of high-grade metamorphic rocks that formed during collision now behave mostly as rigid parts of the continental interior rather than as sites of new intense deformation. The main zones where plates still meet and interact strongly are along the outer margins of the supercontinent, where subduction continues to carry old oceanic lithosphere down into the mantle. In this sense, Columbia acts as a large tectonic lid, a continuous block of thick lithosphere that moves as a unit relative to the deeper mantle, while most of the active shortening and magmatism take place along its edges. The interior of the supercontinent is made up of several old cratonic cores and the collision belts that link them. These regions together form a thick, cool lithosphere that is mechanically strong. Old faults and shear zones remain present, and in places they reactivate under new stresses, but compared with the earlier assembly stage, the amount of internal deformation is smaller and more localized. Large tracts of the interior experience long periods without major mountain building events. Instead, the dominant processes in many areas are erosion of existing uplands, slow subsidence of broad basins, and the accumulation of sediments that blanket older structures. These basins may lie above cooled sutures, or within the central parts of cratons where small changes in lithospheric thickness or density allow the crust to sag gently over long timescales. Within them, layers of sand, mud, and carbonate sediment build up, preserving a record of surface conditions during this relatively stable tectonic phase. At depth, the thick lithosphere of Columbia influences how heat moves from the mantle to the surface. Because the supercontinent is large and has deep, cool roots, it acts as an insulating cover over the mantle below. Heat from both the mantle and radioactive decay in the crust tends to accumulate under the continent. Over tens to hundreds of millions of years, this can warm parts of the lower lithosphere and upper mantle beneath the interior. The exact pattern of this warming is uncertain, but it likely varies from place to place depending on the thickness of the lithosphere and the distribution of older collision belts and cratonic roots. In some regions, the warming is expressed by modest episodes of magmatism within the interior of the supercontinent. These intraplate magmatic events may form large bodies of granitic rock and generate extensive volcanic fields that are not directly tied to plate boundaries. When such magmas rise and solidify within the crust, they add new material and locally modify the strength and composition of the lithosphere. However, these events are scattered in space and time and do not in themselves break the overall mechanical integrity of the supercontinent. The global pattern of plate motions during this stage may also differ from earlier times. Some studies suggest that average plate speeds are lower in this interval than in parts of the Archean or in later Phanerozoic times, although this remains a topic of research and is not yet firmly resolved. What is clear from the rock record is that the number of large new collision belts formed in this time window is limited compared with the intervals before and after. Many continents show evidence for long-lasting magmatic and tectonic activity along margins, but relatively few new high-strain belts that cut across the interiors of cratons. This supports the view that Columbia's main outline and internal arrangement remain comparatively stable for several 100 million years. The stable lid behavior of Columbia also influences how stress is distributed within the lithosphere. Because the supercontinent is thick and mechanically strong, forces arising from mantle convection and from slab pull at the margins tend to be transmitted across long distances. Old zones of weakness, such as inherited faults and sutures, may localize some deformation, but large parts of the interior undergo only gentle warping and limited faulting. This helps preserve the earlier geological record inside the supercontinent, since older belts and cratonic nuclei are not overprinted by many new large-scale tectonic events. At the same time, the persistence of long subduction zones around the margins allows the system of plate boundaries to remain active without requiring major changes in the interior. Subduction continues to recycle oceanic lithosphere, build magmatic arcs, and produce new crust at the edges of the supercontinent. The balance between these peripheral processes and the relative calm inside Columbia is a key feature of this stage of its life. Sedimentary basins within the interior respond to this balance. Some basins develop above flexed parts of the lithosphere near the margins, where the weight of outer mountain belts and magmatic additions causes the crust to bend and create space for sediment to accumulate. Others form farther inland as gentle thermal subsidence takes place after earlier episodes of heating. These basins can be very long-lived, receiving sediments over extended periods with only minor interruptions from tectonic uplift. The resulting rock sequences are thick and laterally extensive but often show limited structural disruption, reflecting the low intensity of internal deformation. When later geologists examine such successions, they see long intervals during which the main record is of steady deposition, rather than frequent changes in tectonic regime. The presence of Columbia as a stable tectonic lid thus shapes both the deep and shallow architecture of the continental crust during this mid-Proterozoic interval. Thick old lithosphere in the interior cooled collision belts and widely developed sedimentary basins together define a supercontinent that maintains its basic structure over hundreds of millions of years, while the most vigorous tectonic activity remains concentrated along its outer margins in contact with the surrounding superocean. In many reconstructions that use paleomagnetic data and geological matches between continents, the positions of the main cratons within Columbia during this time shift only slightly from one model to another, reinforcing the picture of a slowly drifting but long-lived arrangement. In this way, the mid-Proterozoic stage of Columbia's history is marked more by continuity and gradual adjustment than by frequent large-scale reorganization of its continental interior. Deep within the joined landmass of Columbia, far from the active subduction margins and magmatic arcs, the continental interiors pass through long periods of quiet surface evolution. The crust beneath these interiors is thick and cool, made of old cratonic cores stitched together by ancient collision belts that have now largely ceased to deform. At the surface, this stable foundation supports broad regions of low to moderate relief. There are uplands where the rocks of old origins and cratons still stand a little higher, and there are basins where the crust has sagged and created space for sediments to accumulate. But there are relatively few sharp, newly formed mountain belts cutting across the interior during this stage. Over millions of years, weathering and erosion work slowly on the exposed rocks. Chemical weathering breaks down minerals at or near the surface, especially in warmer and wetter climatic zones. Feldspars and mafic minerals alter to clays and iron oxides, while quartz tends to survive and move as sand. Physical processes such as frost wedging in cooler regions or thermal stress in hot, dry areas help break rock into smaller pieces. Rivers gather these products of weathering and carry them from higher ground toward lower central areas and toward the continental margins. The result is a gradual reduction of relief as high areas are cut down and low areas are filled in. In many parts of Columbia's interior, this process leads to the development of broad, subdued landscapes with widely spaced hills, gentle slopes and extensive plains. Where basins form subsidence allows thick packages of sediment to build up. Some basins lie above cooled sutures and form orogenic zones where the crust is thicker and still slowly relaxing after earlier compression. Others develop above parts of the cratonic interior where small changes in lithospheric density and thickness promote gentle downward flexure. In either case, the rate of subsidence is usually low when viewed on short timescales, but significant over tens or hundreds of millions of years. As sediments pile up, they compact and lithify, creating layered sequences of sandstone, mudstone, shale, and carbonate rocks. In some regions, long-lived rivers feed deltas and alluvial plains that advance into these basins, building laterally extensive sheets of sand and mud. In others, shallow lakes and inland seas occupy parts of the basins, depositing fine-grained sediments and evaporate minerals under appropriate conditions. Soils develop on the exposed surfaces between episodes of burial, recording intervals of surface stability. The repeated alternation of deposition soil formation and renewed deposition leaves a subtle but important record in the rock columns of these basins. Surface water systems in the interior adjust to the slow changes in topography and basin geometry. Large river networks drain significant portions of the supercontinent, flowing from interior uplands towards subsiding basins, and in some cases continuing onward to the distant coasts. Because the land mass is broad, some drainage systems may be entirely internal, for long periods feeding lakes and enclosed basins rather than reaching the surrounding superocean. In arid regions, ephemeral streams carry sediment only during rare heavy rains, leaving behind fans and sheet deposits of coarse material along the fronts of local uplands. In more humid regions, perennial rivers carve valley networks and meander across floodplains, leaving behind stacked point bar sands and overbank muds. Groundwater percolates through weathered zones and porous sediment layers, further altering minerals and transporting dissolved substances. The chemical composition of these fluids helps control which minerals are stable at shallow depths, and which are removed or redeposited elsewhere. In some settings, prolonged interaction between groundwater and reactive rocks leads to deep weathering profiles with thick zones of altered material overlying more preserved bedrock. Such profiles can become important markers of ancient land surfaces when later buried and preserved. The climate over the interior of Columbia is influenced by the supercontinent's size and by its position relative to the equator, but during much of this interval, there is no strong evidence for widespread extreme glaciation affecting the entire landmass. Instead, many sedimentary records from this time suggest relatively moderate and long-lived conditions with stable patterns of temperature and rainfall on very long time scales. This does not mean that there are no regional differences or shorter climatic shifts, but the rock record in many basins indicates extended periods of similar depositional environments. Thick sequences of shallow water, carbonate rocks, and fine-grained silica-clastic sediments with relatively few interruptions by coarse glacial deposits or signs of abrupt climatic extremes support this view. In such a setting, interior basins can persist for very long durations, accumulating hundreds to thousands of meters of sediment with only modest tectonic disturbance. Within these basins and across the low-relief interiors, biological activity is present but remains dominated by microbial life. On land, microbial communities colonize soil surfaces, weathered rock, and possibly some moist environments such as transient ponds and streams. In shallow lakes and inland seas, photosynthetic microorganisms play a role in local oxygen production and in the cycling of carbon and nutrients. Where conditions are right, microbial mats can form layered structures in carbonate-rich waters, building modest stromatolitic mounds along shorelines and in shallow subtidal zones. These structures generally less abundant and less diverse in purely continental interiors than along broad marine shelves, but they still contribute to the overall pattern of life at the surface. The long durations of relative tectonic calm in many interior regions allow surface processes to operate without frequent resets from mountain building or large-scale faulting. As a result, unconformities that form in these settings often mark gradual changes in sediment supply or base level rather than sudden tectonic upheaval. Gaps in deposition may reflect times when erosion slightly outpaces subsidence, or when climate shifts reduce sediment delivery. When deposition resumes, new layers may rest nearly flat upon older ones, making it clear that large tilting or folding has not intervened. This style of stratigraphy, with extensive gently deformed sequences separated by broad low-angle unconformities, is a hallmark of many Proterozoic interior basins, and fits well with the idea of Columbia as a long-lived stable supercontinent during this part of its history. At greater depth beneath these quiet surface landscapes, the crust and upper mantle continue to evolve thermally and mechanically. Heat produced within the crust and arriving from below causes slow adjustments in density and viscosity. In some regions, this may lead to mild uplift or subsidence, without strong deformation of the overlying rocks, a process often called a pyrogenic movement. Such vertical motions can redirect drainage patterns and shift the focus of sedimentation within basins, yet they do not generate the intense folding and faulting characteristic of active origins. Instead, they gently reshape the broad surface of the interior over long timescales. Taken together, these processes define the character of Columbia's continental interiors during this stage. Old thick lithosphere supports wide low-relief regions where weathering, erosion and sedimentation dominate. Long-lived basins collect thick sedimentary fills with relatively simple structures. River systems and shallow lakes adjust slowly to changes in relief and subsidence. Microbial life participates in surface chemistry, but does not yet drive rapid, large-scale changes in the appearance of the land. The tectonic framework that controls these conditions remains the presence of a large, stable supercontinent, whose main zones of intense deformation lie at its distant margins, while its heartlands continue to evolve through patient surface processes and gentle vertical motions rather than frequent major tectonic events. At the outer edges of Columbia, the quiet continental interiors give way to more rugged ground, where highlands, basins, and broad shallow seas meet the surrounding superocean. Here the surface of the supercontinent is shaped by the interaction between old mountain belts, active convergent margins, and the long, gently sloping shelves that extend under seawater away from the land. Moving outward from the interior rivers that cross low plains and basins begin to converge into larger trunk systems. These rivers carry sand-silt clay and dissolve material eroded from the uplands that mark ancient or ongoing collision zones. As they approach the margins, the landscape becomes more varied. In some sectors, remnants of major mountain belts rise as long ridges and plateaus. In others, uplifted but more subdued hills mark older origins that have already lost much of their original relief. At the foot of these uplands, narrow foothill zones grade into wide foreland basins, where the weight of the mountains has caused the crust to sag and create room for thick piles of sediment. Within these foreland basins, rivers deposit coarser material closer to the mountain front and finer material farther out. Alluvial fans and braided river systems lay down sheets of gravel and sand near the foothills. Farther basinward, meandering rivers and floodplains spread mud and fine sand across broad lowlands. Over time, lakes and shallow inland seas may occupy parts of the basin, depending on local subsidence and sea level. These water bodies receive fine-grained sediments and sometimes evaporate minerals if the region is restricted and evaporation is strong. The layers that accumulate here form thick successions that record the gradual wear of the mountain belts and the steady sinking of the foreland region. Crossing the outer edge of the foreland, the land surface often transitions into low coastal plains, and then into shallow seas that extend far out over the continental shelf. Along many stretches of Columbia's margin, the shelf is broad because the continent is large and its edges have subsided gradually over time. The water over these shelves is generally shallow compared with the open ocean, and light can reach the seafloor in many places. In such environments, a mix of siliciclastic and carbonate sediments is laid down. Near river mouths, deltas prograde into the sea, forming thick wedges of sand and mud that build outward from the coastline. Between major river systems where water is clearer and sediment input from land is lower, carbonate platforms can grow. These platforms form from the accumulation of chemical precipitates and the remains of microbial communities that live on or just below the seafloor. The result is a patchwork of sandy deltas, muddy shelves and carbonate banks along the rim of the supercontinent. Beyond the shelf, the seafloor slopes more steeply down the continental slope and into the deeper parts of the ocean basin. Gravity-driven flows called turbidity. Currents carry sediment from the shelf edge down the slope and out across the continental rise, forming submarine fans. These fans spread sand and silt over wide areas at depths where little light reaches. In regions where active subduction zones lie close offshore trenches mark the deepest parts of the margin. There, sediments from the shelf and slope can be scraped off the downgoing plate and added to the overriding plate, contributing to accretionary prisms and complex belts of deformed rocks at the seaward edge of the continent. The presence or absence of such trenches and prisms varies along the margin depending on the exact configuration of plate boundaries. The mountain belts along the active parts of Columbia's rim are built and modified by the ongoing convergence recorded in these offshore and nearshore features. Where subduction continues, magmatic arcs stand inland from the trench, adding new volcanic and plutonic rocks to the margin. These arcs may rise high above the surrounding terrain, feeding large volumes of sediment into adjacent foreland basins as they erode. In places where older collision belts now lie within the outer parts of the continent, but subduction has migrated outward, 2 or more generations of mountain building can be stacked across the margin. The resulting topography is complex with multiple ridges and intervening basins that together grade toward the coastal lowlands and shelves. In contrast, some segments of Columbia's edge behave more like passive margins during parts of this interval. In these areas, there is no nearby subduction zone, and the crust along the margin is stretched only slowly. Subsidence is gentle and long-lasting, and thick packages of shelf sediments accumulate with relatively little deformation. Large deltas and shallow marine systems can migrate back and forth across these margins as sea level and sediment supply change, leaving behind layered records of marine flooding and regression. Even in these quieter segments, the broad shape of the margin still reflects the overall structure of the supercontinent, with thick continental lithosphere stepping down into the thinner oceanic crust of the superocean. The distribution of shallow seas around Columbia is controlled by both tectonic subsidence and global and regional changes in sea level. When sea level rises relative to the land, epicontinental seas can spread far inland over low-lying areas near the margins. These seas form extensive shallow water environments that may cover thousands of kilometers of the continental surface. When sea level falls or the land is uplifted slightly, shorelines move seaward and rivers incise into previously flooded regions. In the rock record, these shifts appear as vertical successions in which shallow marine deposits alternate with more terrestrial or coastal sediments. Over long intervals, repeated cycles of transgression and regression stack multiple such sequences built on the slowly subsiding framework of the margin. Sediments deposited along the margins are not simply passive records. They also influence how the crust responds to loading and unloading. Thick sedimentary wedges add weight to the edges of the continent, enhancing subsidence in some basins and promoting further accommodation space for more sediment. At the same time, erosion of mountain belts removes mass from the uplands, allowing them to rebound slightly. This balance between erosion, sedimentation, and flexure helps keep fallen basins active over long periods and maintains the contrast between upland ranges, lowland basins, and shallow seas at the rim of the supercontinent. The combined effect of these processes is a dynamic but not chaotic margin system. High ground along collision belts and active arcs feeds sediment into basins that fringe the mountains. These basins grade into wide coastal plains and shelves, which in turn pass into deeper marine environments, and in some sectors into trenches and accretionary complexes at subduction zones. The details vary from one segment of Columbia's perimeter to another, but the general pattern is consistent. The outer zones of the supercontinent are the main interface where land-shallow seas and the surrounding superocean meet and interact. Over hundreds of millions of years, this interface shifts position, builds and erodes topography, and stacks thick successions of sedimentary and volcanic rocks that later preserve the imprint of Columbia's margins in the geological record. Around Columbia, the global ocean, the atmosphere and the climate form a linked system that changes slowly over very long timescales. The supercontinent sits within a single broad superocean that wraps almost completely around its margins. Surface currents in this ocean are guided by wind patterns, by the position of the equator and the poles, and by the shape of the continental outline. Where warm surface waters are driven away from the equatorial regions, cooler waters rise from depth to replace them, bringing dissolved nutrients toward the light. In higher latitudes, cold, dense surface waters sink and begin long paths through the ocean interior. This circulation of surface and deep water, sometimes called thermohaline circulation, when driven by both temperature and salinity differences, helps distribute heat and dissolved substances around the globe. However, the exact structure of these currents in the Middle Proterozoic is not directly known. Instead, it is inferred from general physical principles and from chemical signatures preserved in ancient marine rocks. The chemistry of the ocean during Columbia's tenure reflects both the composition of the atmosphere and the rate at which elements are supplied from land and from mid-ocean ridges. After the earlier rise in atmospheric oxygen, shallow surface waters near the continents are more oxygen-rich than in Archean times, especially where photosynthetic microorganisms are active. Farther offshore and at greater depth, large parts of the ocean remain poorly oxygenated, and in some regions deeper waters may contain dissolved iron and sulfide. This leads to vertical and horizontal gradients in redox state, meaning that some layers are more oxidizing and others more reducing. Sedimentary rocks from this interval, including iron formations, manganese deposits, and certain types of sulfur, rich shales, record these redox patterns. They indicate that oxygen has become an important part of surface environments, but that the deep ocean is not yet fully oxygenated in a way similar to modern oceans. The atmosphere above Columbia contains more oxygen than in Archean times, but still less than in later eras. Estimates of its exact concentration vary, but many studies suggest that it is a significant fraction of the present level, rather than a trace. Carbon dioxide in the air remains higher than in most later Phanerozoic times. It plays a major role in keeping Earth's surface warm since the Sun at this time outputs less energy than it does in the present. The balance between volcanic emissions of carbon dioxide, its removal by weathering of silicate rocks on land, and its storage in marine carbonate sets the long-term level of this greenhouse gas. The extensive land area of Columbia, with its wide zones of exposed granitic and metamorphic rocks, provides a large surface for chemical weathering. When rain falls on these rocks, it reacts with minerals consuming carbon dioxide dissolved in the water and carrying bicarbonate and other ions to the ocean. There, these ions can be incorporated into carbonate minerals that settle to the sea floor. Over long timescales, this process, together with the return of carbon dioxide to the atmosphere through volcanic degassing, helps keep global climate within a range that allows liquid water to persist on the surface. The arrangement of land and sea has a direct influence on climate as well. A large supercontinent like Columbia modifies atmospheric circulation compared with a world of many smaller continents. Air masses that cross the wide superocean pick up moisture and heat before reaching the continental margins. When they rise over coastal uplands and mountain belts, they lose moisture as rain or snow feeding big river systems, and in some regions providing conditions for chemical weathering to proceed rapidly. As air moves further into the continental interior, it becomes drier. Some interiors may develop more arid climates, especially if they lie far from coasts and at certain latitudes. However, because the precise positions of Columbia's cratons with respect to the equator and the poles are still under study, the detailed distribution of climate zones across the supercontinent remains uncertain. Geologists infer general patterns from the types of rocks preserved. Thick successions of shallow marine carbonates point to warm, clear waters in many shelf regions. Red beds, which are oxidized sandstones and mudstones, suggest subaerial exposure and oxidizing conditions on land in some areas. The relative scarcity of widespread glacial deposits in this time interval, compared with units from much earlier and much later, supports the view that there are no long-lasting global-scale glaciations affecting all latitudes during much of Columbia's stable life. Instead, climates appear to have been comparatively moderate over very long periods, with possible regional ice in some high-latitude regions, but no strong evidence for continent-spanning ice sheets at low latitudes in this specific interval. The stability of climate over these long spans is also reflected in the behavior of certain isotopic systems, such as carbon isotopes in marine carbonates. During much of the Middle Proterozoic, these records show limited large swings compared with some other times in Earth's history. This pattern has led some researchers to refer informally to this interval as a boring billion years in terms of apparent environmental variability. The word here does not refer to the importance of the time, but to the relative steadiness of some signals. The use of this phrase does not exclude smaller scale changes, it simply reflects the lack of frequent, very large globally recorded excursions in many proxies during this time. Within this overall framework of moderate climate conditions along Columbia's margins and interiors still vary. Coastal regions facing the superocean experience strong interactions between ocean currents and atmospheric systems. Monsoon-like circulations may develop where large seasonal differences in heating between land and sea exist, bringing wet and dry seasons to some parts of the supercontinent. Inland basins record local climate in the balance between river-supplied sediments, lake levels, and evaporation. Evaporate deposits in some sequences indicate times when evaporation in restricted basins outpaces inflow, leading to the precipitation of salts. The combination of rock types, sedimentary structures, and fossils of microbial life in these sediments allows paleoclimatologists to reconstruct general aspects of ancient temperature and rainfall patterns, although many details remain uncertain. The superocean that surrounds Columbia helps buffer global temperatures by distributing heat. Warm waters flowing toward higher latitudes release heat to the atmosphere, while cold currents moving toward the equator absorb heat. This reduces temperature contrasts between equatorial and polar regions compared with a world with less vigorous circulation. The absence of large land masses at certain latitudes also matters, because continents can support ice sheets more easily than open ocean. In the interval during which Columbia is stable, the combined effect of these factors is a climate system that appears relatively steady on very long timescales. Local and regional variations certainly occur driven by plate motions, changes in sea level volcanic episodes, and possible slow shifts in atmospheric composition. But the broad picture is one of a world in which the oceans, atmosphere, and climate operate in a mode that does not disrupt the long-term existence of the supercontinent. In this setting, the interaction between weathering of Columbia's rocks, transport of dissolved and solid material to the superocean, and deposition of marine sediments maintains a slow but persistent exchange of chemicals between land, sea, and air. The atmosphere remains oxygen-bearing but not yet fully modern in composition. The oceans are partly oxygenated near the surface, but still feature large regions of low oxygen water at depth. The climate is warm enough to keep most of Earth free of permanent low-latitude ice. All of these conditions together define the environmental backdrop against which life and surface processes continue to operate during the long middle part of Columbia's existence. During the long middle part of Columbia's life, the surface of Earth is already inhabited, but the living world is made almost entirely of microorganisms. The interiors and margins of the supercontinent are shaped at the surface by weathering, erosion, and sedimentation, and these physical processes are closely linked to the activity of microbial life in water and on land. There are no land plants, no animals, and no forests. Instead, life is concentrated mainly in the oceans, in shallow seas along the margins of Columbia, and in thin communities that occupy some moist surfaces on and near the supercontinent. In the global ocean that surrounds Columbia, photosynthetic microorganisms in the upper sunlit layer form the base of marine ecosystems. Many of these organisms are cyanobacteria, which are bacteria that use light water and carbon dioxide to make organic matter and release oxygen. Alongside them, simple eukaryotic cells are present. A eukaryote is a cell with a nucleus and internal compartments. The earliest clearly preserved fossils of such cells occur in Proterozoic rocks, and during the time when Columbia is stable, these simple eukaryotes live in the water column and on the sea floor together with bacteria and other microorganisms. In shallower marine settings, especially on the broad continental shelves around Columbia, dense microbial mats grow on and within the surface sediment. These mats are layered communities of microbes that trap and bind sediment grains, and can also promote the precipitation of minerals. In carbonate-rich waters, their activity leads to the growth of stromatolites. A stromatolite is a layered structure made of sediment and minerals held together by microbial mats. Each layer forms as microbes grow, trap small particles, and induce mineral growth, creating domes, columns, or flat laminated bodies. On the shallow shelves and tidal flats that fringe Columbia, stromatolitic buildups and related microbial structures are common features. They grow slowly, recording long intervals of relatively stable conditions in these shallow seas. The appearance and abundance of stromatolites change through time, but during the mid-Proterozoic, they remain important recorders of shallow marine life and sediment interaction. The chemistry of the water around these communities is shaped by both biological activity and inputs from land. Rivers that drain Columbia carry dissolved ions, such as calcium, magnesium, bicarbonate, silica, and various nutrients into the ocean. These ions come from the chemical weathering of rocks on land, which is itself influenced by climate rock type and microbial processes in soils and at the rock surface. When these dissolved materials reach shallow seas, they contribute to the formation of carbonate minerals, chert, and other chemical sediments, as well as feeding the metabolism of planktonic and benthic microorganisms. In regions where nutrient input is relatively high, and circulation brings deeper nutrient-rich waters back toward the surface, productivity in the phytic zone can be enhanced, supporting larger populations of photosynthetic microbes and their consumers. Below the sunlit layer, the water column and seafloor host other metabolic types. In zones where oxygen levels drop, microbes use alternative electron acceptors to break down organic matter. Some use sulfate to carry out sulfate reduction, producing sulfide as a byproduct. Others may use nitrate ion or other compounds. In the deepest parts of the ocean, and in some restricted basins along the margins of Columbia, bottom waters can become low in oxygen, or even anoxic. In such settings, organic matter is more likely to be preserved in sediments, and minerals containing iron and sulfur may form. The result can be the accumulation of organic-rich shales and sulfur-bearing rocks that record intervals when deep waters or basin interiors were poorly oxygenated. These rocks are later key indicators of the balance between oxygen production in surface waters and oxygen consumption at depth. On the continental shelves around the supercontinent, the mix of microbial life sediment supply and water chemistry produces varied sedimentary facies. In clear, warm, shallow seas with low input of triginous mud and sand, carbonate platforms grow by the accumulation of lime mud and skeletal or framework structures created by microbes and simple eukaryotes. Layered stromatolites, microbial mounds, and laminated carbonates build up over long timescales, sometimes forming thick successions. Where rivers deliver more siliciclastic sediment, microbial mats and communities adapt to muddier or sandier conditions, stabilizing tidal flats, shallow subtidal bars and delta fronts. In both types of settings, the interaction between living mats and moving water helps organize sediment into distinctive structures such as wrinkled bedding, roll-up features, and fine lamination. These features preserved in rock give later geologists clues about the presence and behavior of microbial surfaces on and around Columbia. On land, life is more sparse but still present. Microbial communities occupy moist soils, weathered rock surfaces, and perhaps some areas near lakes, rivers, and coastal zones where water is available at least part of the time. These communities can influence the rate and style of chemical weathering by producing organic acids and by altering the redox state of elements in the rocks and soils they inhabit. In some places, thin biological soil crusts may form binding loose sediment grains together and reducing erosion by wind. Such crusts are not preserved directly in most ancient rocks, but their modern analogues help illustrate how microbial life can alter the surface of a continent even in the absence of higher plants. The combined effect of microbial life in soils and on rock surfaces together with physical weathering is to increase the supply of dissolved ions and fine particles to rivers. This enhances the delivery of nutrients such as phosphorus and nitrogen compounds to the ocean. In turn, this nutrient supply supports primary production by marine microbes, linking the land-based processes on Columbia to the productivity and oxygen production of the surrounding seas. The burial of organic carbon produced by photosynthesis is a key factor in the long-term rise of oxygen in the atmosphere. When organic matter is buried and preserved in sediments rather than fully oxidized back to carbon dioxide, oxygen generated by photosynthesis can accumulate. During the time when Columbia is stable, many basins around its margins and in its interior receive fine-grained sediment that can preserve organic matter, especially where bottom waters are low in oxygen. The extent and rate of this burial are still under study, but the presence of organic rich shales in Proterozoic sequences shows that significant amounts of carbon are stored in the sedimentary record. This storage interacts with weathering and volcanic degassing to set the long-term balance of oxygen and carbon dioxide in the atmosphere. In addition to carbon and oxygen, microbial activity affects the cycles of sulfur ion and other elements. Sulfate reducers in anoxic environments convert sulfate to sulfide, which can combine with iron to form sulfide minerals. Oxidizing microbes can then act on these compounds when conditions change, leading to complex patterns of mineral growth and dissolution. Ion cycling involves bacteria that can oxidize or reduce iron helping control, whether it remains dissolved in water or precipitates as iron oxides and other minerals. These processes leave their mark in the isotopic composition of sulfur carbon and other elements preserved in sedimentary rocks, providing further evidence for the types of metabolisms that existed during Columbia's tenure. The diversity of microbial metabolisms in the ocean and on land allows the global system to recycle key elements, even in the absence of complex plants and animals. Hydrothermal vents along mid-ocean ridges and in back-arc basins supply reduced compounds such as hydrogen, methane, and metal-rich fluids to the deep ocean, where chemosynthetic microbes use them as energy sources. These deep communities exist largely independent of sunlight, yet they are linked to the broader ocean through the movement of water and dissolved substances. On the shelves and in the photic zone, photosynthetic microbes capture solar energy and form the primary source of organic matter for heterotrophic microbes that consume it. Together, these communities maintain a steady throughput of energy and matter through the biosphere. In this way, life and surface processes during Columbia's existence form a tightly connected system. Weathering of the supercontinent's rock supplies dissolved ions and nutrients to the ocean. Marine and terrestrial microbes use these materials to build biomass and to carry out redox reactions that influence the chemistry of water and air. Burial of organic matter and minerals in sediments removes some substances from short-term cycles and stores them in the crust. Over very long timescales, tectonic uplift and erosion return these materials to the surface, where they can again be weathered and cycled. Throughout this interval, the biosphere remains microscopic in form, but significant in effect, participating in the slow, steady regulation of Earth's surface environment, while Columbia persists as a large, stable supercontinent surrounded by a wide, partly oxygenated ocean. In the present world, the main physical traces of Columbia are not preserved as a single intact supercontinent, but as scattered pieces in the oldest parts of many continents. These pieces are the cratons and shields that expose ancient rocks at the surface. A shield is an area where very old crystalline rocks, such as granites and metamorphic rocks, are not deeply buried by younger sedimentary layers. Today such shields stand in parts of what are now North America, Northern Europe, Siberia, India, Australia, South America, and Africa. When geologists study these regions, they see that the rocks keep a record of the time when Columbia forms lives and begins to change. Inside each shield, the rock record is arranged in layers and structural blocks. At the base are the oldest units, often Archean in age, which formed long before Columbia. Above and around these cores lie younger belts and intrusions that date from the Paleo-Proterozoic and early Mesoproterozoic. These younger rocks include thick packages of deformed sedimentary and volcanic rocks, large bodies of granitoid rock, and regions of high-grade metamorphic rock. Many of these units have ages between about 2 billion, 100 million, and 1,500,000,000 years, the same broad interval in which Columbia assembles and persists. This match in age and style is one of the main reasons geologists link them to the supercontinent. To read this record, geologists rely on field mapping and on radiometric dating. Radiometric dating is a method that uses the known rate of decay of radioactive elements in minerals to determine when a rock or mineral formed or cooled. One of the most useful minerals for this purpose is zircon, which can survive many later events and still keep an internal record of its age. By sampling zircons from igneous rocks such as granitoids, and from sediments that were derived from older crust, geologists can find out when magma crystallized, or when source rocks were eroded. When many rocks from a given belt or province show ages that cluster in the interval of Columbia's assembly, it is likely that this area was active during that time. In several cratons, long belts of deformed rocks with these ages run across large regions. They separate older Archean cores from one another, or lie along the edges of those cores. Their structural patterns, rock types, and ages indicate that they formed as collision belts and active margins during the building of Columbia. In what is now Central and Northern North America, for example, belts of Paleoproterozoic rocks link separate Archean blocks into a continuous region. In parts of what are now Northern Europe, Siberia, India, and Australia, similar belts of comparable age occur. Although the exact details differ, the overall picture is that many shields preserve wide zones of deformation and magmatism that were active when Columbia came together. Above and beside these belts, large regions contain granitoid intrusions of similar age. These intrusions formed when the crust melted partially during collision or subduction-related magmatism. Their presence shows where thickened crust and active magmatic arcs once existed. When such granitoid provinces are found on more than one present continent and share similar ages and chemical characteristics, they suggest that these areas once lay near the same parts of Columbia's margin or interior. In some cases, sedimentary basins also preserve the record of Columbia's life. After collision and mountain building, erosion of high ground produced sediments that filled fallen basins and interior basins. These sediments include sandstones, mudstones, and conglomerates that contain fragments and grains derived from the newly formed belts and older cores. Detrital zircons in these sediments often show age patterns that match the underlying crust. For example, a sandstone may contain zircons with Archean ages that match an old core, and Paleoproterozoic ages that match nearby collision belts. This combination suggests that the basin lay near those sources at the time of deposition. When similar age patterns appear in basins on different continents, they support links between those regions during Columbia's existence. Some basins also contain thick sequences of shallow marine carbonate rocks and fine-grained siliciclastic rocks that were laid down during the more stable parts of Columbia's history. These sequences often show little structural disruption and only gentle metamorphism consistent with their formation in interior or marginal basins during a time of tectonic calm. Their ages determined by radiometric methods and by the ages of detrital minerals place them within the long lifespan of the supercontinent. Together with the collision belts and granitoid provinces, they show that Columbia is not just an abstract idea, but that its presence is recorded in the layered arrangement of rocks and the ages of minerals in many shields. Another kind of evidence comes from the way structural trends in different shields relate to each other. In some reconstructions, belts of similar age and orientation on separate continents can be aligned to form longer continuous zones when the continents are moved into new positions on a reconstruction map. For example, a Paleoproterozoic belt that trends in one direction in present North America may line up with a belt of similar age and direction in present Northern Europe if those continents are brought together. This does not by itself prove that they were once joined, but when combined with matching ages, rock types and sediment patterns, it strengthens the case that these belts once formed part of a continuous orogenic system within Columbia. In addition, the presence of similar sequences of events in widely separated cratons supports the idea of a linked history. Many shields show an early phase of arc building and accretion, followed by a main period of collision and thickening, and then a later period of cooling, erosion and basin development. The absolute ages of these phases vary somewhat from place to place, but they often fall within the same broad windows. This pattern suggests that a global scale process such as the formation and long existence of a supercontinent influenced tectonic activity across many regions at roughly the same times. The geological record also shows that the life of Columbia extends into the Mesoproterozoic. Some granitoid intrusions, sedimentary basins, and mild deformation events in shields have ages between about 1,600,000,000 and 1,300,000,000 years. These features may record later adjustments within the supercontinent, minor internal reorganization or renewed activity along certain margins. They show that Columbia does not stay completely unchanged during its long life, but passes through quieter phases and more active phases while still maintaining a basic joined structure. Through this time, the main record continues to be preserved in the ancient crustal blocks that now stand as separate continents. In addition to the rock belts, basins, and intrusive provinces that record Columbia's assembly and long life, another set of clues is preserved in the magnetic properties of rocks and in the pattern of long, dark, igneous intrusions that cut the ancient crust. Together, paleomagnetic data and mafic dike swarms help geologists estimate how different cratons are oriented and where they lie in latitude when Columbia exists. Paleomagnetism is the study of the remanent magnetization of rocks. When some igneous rocks cool from a melt iron bearing minerals within them, can align with Earth's magnetic field and lock in that direction as they pass below a certain temperature. When some fine-grained sediments are laid down, tiny magnetic grains can also align with the field as they settle, so that after the sediment hardens, the rock keeps a record of the direction of the field at the time of deposition. If the field behaves on average over a suitable time interval like a simple dipole aligned with Earth's rotation axis, then the direction recorded in the rock can be used to estimate the latitude at which the rock formed and the apparent position of the magnetic pole at that time. To use this information, geologists collect oriented samples from suites of rocks of known age. They then measure the direction and strength of the remanent magnetization in the laboratory. The directions from many samples in a single unit are combined to give a mean direction, which can be converted into a paleomagnetic pole. When similar age poles from one craton and from another craton are compared, the positions of the cratons can be rotated until their poles coincide. This procedure gives a possible relative orientation and latitude for the cratons at that time. When poles of different ages are linked in time sequence for a single craton, they form an apparent polar wander path, which traces how that craton moves relative to the spin axis through time. For Columbia, paleomagnetic data from several cratons fall in the broad interval between about 2,100,000,000 and 1,300,000,000 years ago. Rocks that carry magnetizations of these ages include basaltic lava flows, dike swarms, some volcanic lastic units, and some sedimentary rocks that have not been heated or chemically altered too much since they formed. From these units, paleomagnetic poles have been derived for parts of what are now Laurentia, Baltica, Siberia, North China, India, Australia, and South America. When these poles are plotted and paths are drawn through them, they suggest that many of these cratons share linked motions during the time when Columbia assembles and persists. However, the paleomagnetic record of this age range is incomplete and subject to several kinds of uncertainty. In some regions, rocks of the right age are poorly exposed or have not yet been sampled in detail. In others, Heating during later metamorphism or intrusions has reset the magnetic signal, so that the recorded direction reflects a younger event rather than the original time of rock formation. To judge the reliability of a magnetization, geologists carry out tests in the field and in the laboratory. A fold test asks whether the magnetization directions in a deformed rock unit become better grouped when the layers are mathematically restored to their original unfolded positions. If they do, the magnetization likely forms before folding and may record the original field. A conglomerate test examines whether clasts in a conglomerate have random directions. If they do, the magnetization probably predates the cementation of the conglomerate. In the laboratory, stepwise heating or application of alternating magnetic fields is used to separate stable ancient components from younger overprints. Only magnetizations that pass such checks and that are tied to well-constrained rock ages are used as key poles for reconstructing Columbia. Even with these precautions, paleomagnetic poles have uncertainties in both position and age. As a result, more than one arrangement of cratons can satisfy the same sets of data within error. Some models place certain cratons side by side while others separate them by narrow oceans, depending on how specific poles and paths are interpreted. These differences are one reason why modern reconstructions of Columbia or Nuna differ in details about the exact outline and internal arrangement of the supercontinent, even though they broadly agree that a large joined landmass exists in this interval. Mafic dike swarms provide another kind of geometric information that can be combined with paleomagnetism. A mafic dike is a roughly planar body of dark magnesium, an iron-rich igneous rock that intrudes pre-existing crust along a fracture or zone of weakness. Dike swarms are groups of many such intrusions that share a similar age and in many cases a consistent orientation or a pattern that radiates from a central region. They form when the crust is stretched or responds to pressure changes associated with mantle upwelling, allowing magma to rise in sheet-like bodies. Once the dikes solidify, they preserve information about the stress field and regional extension direction at the time of intrusion. In several ancient shields, large mafic dike swarms of Paleoproterozoic and Mesoproterozoic age cut across old cratonic rocks. These swarms can extend for hundreds of kilometers, and sometimes for more than 1,000 kilometers. High-precision radiometric dating of minerals such as baddelite and zircon in these dikes gives ages that can be accurate to a few million years. When age and orientation are both known, dike swarms can act as piercing lines through the crust. If a swarm that originally forms as a continuous system is now split between two or more cratons, its pieces may appear on different continents. By moving the cratons around in a reconstruction until the segments of the swarm line up and share the same age, geologists can find a configuration that restores their original continuity. In this way, dike swarms help link separated shields back into their positions within Columbia. In some cases, paleomagnetic directions measured from the dikes themselves provide an additional constraint on latitude and rotation at the time of intrusion. When paleomagnetic poles and dike swarm matches support each other, confidence in a particular reconstruction becomes stronger. Another set of igneous features, large igneous provinces, also contributes to this picture. These provinces are regions where very large volumes of basaltic magma are erupted or intruded over a relatively short geological interval. They include thick flood basalt sequences and associated dike and sill complexes. Several such provinces have ages between about 1,800,000,000 and 1,300,000,000 years, and are found on more than one present continent. Matching the ages and geochemical signatures of these provinces and aligning associated dike swarms gives further hints about which cratons lie adjacent in Columbia and how they later shift. As with paleomagnetic poles, the interpretation of dike swarms and large igneous provinces comes with uncertainties, Erosion and later deformation can remove or bend parts of swarms, making their original patterns harder to see. Younger intrusions can cut across older ones, complicating the picture. Some provinces may reflect local extension or mantle events that do not affect the whole supercontinent. Geologists therefore use these features together with structural, sedimentary and paleomagnetic evidence, rather than on their own. When these different lines of evidence are assembled, a consistent broad pattern emerges. The distribution and ages of collision belts, magmatic arcs, sedimentary basins, paleomagnetic poles, mafic dike swarms and large igneous provinces all point to a time between roughly 2,100,000,000 and 1,300,000,000 years ago, when many of the world's cratons move together, share linked tectonic and magmatic histories, and then begin to record signs of changing relative motions. Within the limits of the available data, this pattern is consistent with the presence of a long-lived supercontinent, Columbia or Nuna, whose configuration can be outlined in general terms, even though many local details remain uncertain. After a long interval of relative stability, the structure of Columbia begins to change. The thick lithosphere that makes up the supercontinent has acted for hundreds of millions of years as a mechanical and thermal lid over the underlying mantle. Heat has slowly accumulated beneath parts of the interior, and stresses from ongoing subduction around the margins, and from mantle flow beneath the superocean continue to act on the edges and base of the continent. Over time, these forces combine with variations in crustal thickness and inherited zones of weakness to produce regions where the lithosphere stretches instead of compresses. In several sectors of Columbia, this stretching takes the form of rifting. A rift is a zone where the crust and upper mantle are pulled apart, leading to thinning of the lithosphere and subsidence of the surface. The earliest signs of this process appear along old sutures and margins, where the crust is already somewhat weakened by past tectonic activity. Small amounts of extension localize along pre-existing faults which reactivate in a new sense. The surface begins to sag and narrow basins with steep sides develop. In these basins, rivers and lakes deposit sediment eroded from nearby uplands, forming packages of conglomerate sandstone and finer material. Volcanism may accompany the early stages of rifting, as decompression melting in the upper mantle generates basaltic magma that ascends through fractures. As extension continues, some rifts widen and deepen. The crust in these regions becomes thinner, and the mantle lithosphere also stretches. The surface subsides further, turning narrow valleys into broader rift basins. In some cases, long linear lakes or shallow seas form within these depressions depending on their depth and connection to the surrounding ocean. Thick successions of continental and shallow marine sediments accumulate interlayered with volcanic rocks. Large mafic dike swarms and sill complexes intrude the crust, feeding these volcanic episodes. Radiometric ages of many such igneous bodies on present continents fall between about 1,600,000,000 and 1,300,000,000 years, marking this as a time when rifting and related magmatism become more widespread in parts of Columbia. Not all rifts progress to the same stage. Some remain localized and eventually slow down, becoming failed rifts. A failed rift, sometimes called an ola-cosion, is a zone where extension begins but does not continue to the point of creating a new ocean basin. The crust there remains thinned and filled with sediments and intrusions, preserving evidence of the attempt to split, but not leading to full separation. Other rift systems continue to widen, where extension persists and the lithosphere becomes thin enough. Hot asthenospheric mantle rises closer to the surface. Partial melting in this upwelling mantle produces more basaltic magma, which can erupt at the surface or spread out as intrusions at depth. The creation of new oceanic crust in the central parts of these mature rifts marks the transition from continental rifting to seafloor spreading. At this stage, the rift has evolved into a young ocean basin. Once seafloor spreading begins, the two sides of the former rift move apart on opposite plates. The geometry of these new spreading centres and their relation to older sutures and margins determine how Columbia is subdivided. Current reconstructions suggest that large sectors of the supercontinent separate into western and eastern clusters of cratons with narrow oceans opening between them. Some models describe this as a partial breakup in which major blocks move apart, but broad areas of continental crust remain in contact in other regions. Other models emphasize reconfiguration, where extension and rotation adjust the relative positions of cratons without completely dispersing the supercontinent at once. In either case, the geological record shows that by around 1,300,000,000 years ago, the pattern of basins, magmatic belts, and paleomagnetic poles indicates significant relative motion among parts of Columbia. These changes are recorded in several ways. Rift basins formed during this time contain thick accumulations of sediments that differ from older, more stable interior basin deposits. They include coarser material derived from uplifted shoulders along the rift margins, volcanic layers that can be dated, and in marine-influenced settings, evaporites, and shallow marine sediments that show repeated opening and restriction of water connections. The geometry of these basins, often long and narrow, aligns with regional extensional faults that cut earlier structures. Intrusive rocks of similar age, such as mafic dikes and sills, cross-cut older fabrics and in some regions form part of large igneous provinces that spread across wide areas of crust. These igneous features signal increased mantle melting and magma transfer consistent with the onset of extension and thinning. Paleomagnetic measurements from rocks of this age show that some cratons that previously followed similar apparent polar wander paths now begin to record divergent motions. Their poles for the same time intervals no longer line up in a simple way if the cratons are kept in their old relative positions. To reconcile the data, the cratons must be rotated and shifted with respect to one another. This implies that distances between them are changing, and that new plate boundaries have formed within what was once a single tectonic lid. The appearance of young oceanic crust between certain cratons inferred from the ages and types of igneous and sedimentary rocks now found along their facing margins supports this view. The stress field in the lithosphere during this stage is complex. Subduction continues around parts of the remaining supercontinent margins, and slab pull at these boundaries still influences plate motions. At the same time, rising warm mantle beneath certain interior regions of Columbia exerts an upward and outward push on the overlying lithosphere. This combination of boundary forces and basal tractions may help localize extension in particular zones, while other areas remain mechanically coherent. The presence of thick old lithospheric roots under some cratons means that they can resist breakup more strongly than thinner younger belts. As a result, rifting often exploits the margins of cratons and the sutures between them, instead of cutting directly through their most stable cores. Over time, the zones of active extension, magmatism, and subsidence become new structural boundaries that slice Columbia into large fragments. Once fragments begin to drift apart, their margins evolve differently, depending on the new plate configurations. Some newly formed oceans develop simple passive margins on both sides, with little tectonic activity and thick sedimentary wedges building outward from the land. Others maintain or develop subduction zones along one side, turning a former rift margin into an active convergent boundary. These differences lay the groundwork for future tectonic cycles. Within the time frame considered here, however, the main focus is on the initiation and early development of rift systems, and on the geological evidence that parts of Columbia are no longer moving as a single stable unit. In some sectors, extension remains modest, and the continent stays intact. In others, extension proceeds to full rupture, creating new ocean basins and separating large cratonic blocks from one another. The resulting pattern is one in which the long-lived supercontinent passes from a nearly continuous configuration into a more segmented state, with large clusters of continental crust separated by young oceans and linked by zones of complex tectonic activity. The surviving record of these events in present-day shields and basins consists of rift-related sedimentary successions, mafic dike swarms, large igneous provinces, and paleomagnetic paths that together show that Columbia's earlier stability gives way to progressive internal stretching and partial breakup during the late Paleoproterozoic and early to middle Mesoproterozoic. After Columbia has been stretched cut and partly broken into separate blocks, its story does not end abruptly. The cratons and belts that once lay inside a single supercontinent continue to exist as parts of new continental assemblies. Over the long span that follows, these blocks are moved rotated and reattached in different combinations to form younger supercontinents. One of the major later stages is the assembly of a supercontinent commonly called Rodinia, which is thought to come together mainly between about 1,100,000,000 and about 800 million years ago. In many reconstructions, several cratons that once belonged to Columbia are brought together again in new positions to build the core of Rodinia. Old sutures and collision belts that formed during Columbia's assembly are reused as zones where deformation concentrates, or they serve as strong internal backbones around which new belts form. The details of Rodinia's outline and Columbia's exact contribution to it remain under active study, and different models place the same cratons in somewhat different places. However, a consistent theme is that the crust and lithosphere that once made up Columbia do not disappear. They remain as stable blocks and as inherited structures inside younger supercontinents. The reuse of these old structures is a common pattern in Earth's history. When a new collision occurs, the forces involved often exploit pre-existing weaknesses. Old faults, shear zones, and sutures that formed during Columbia's assembly may be reactivated as thrusts or strike-slip faults when cratons move together again in the Rodinia stage. Areas of previously thickened crust can also be thickened further, leading to high-grade metamorphism and partial melting one more time. In some regions, the same crustal slice may record more than one cycle of mountain building with minerals and textures that formed in the Columbia interval, overprinted by those from later events. Geologists use careful field work and radiometric dating to separate these superimposed histories and to identify the different episodes in which a given region was active. After Rodinia, further cycles of breakup and assembly eventually lead to other supercontinents such as Pangaea and later Pangaea. Through these cycles, many of the cratons that were part of Columbia continue to serve as central pieces of larger landmasses. For example, the core of what is now Laurentia, much of Baltica, and other Archean and Proterozoic blocks persist as coherent regions inside these later configurations. The Precambrian shields that are exposed today show this persistence in their internal structure, where very old rocks and belts from Columbia's time sit beneath and beside younger origins from later supercontinent cycles. The modern arrangement of continents still reflects this layered history. The Canadian shield in North America, the Fennoscandian shield in Northern Europe, the cratons of Southern Africa, the North China and Siberian cratons, and the old cores of Australia and South America all contain rocks that were already ancient when Columbia came together and that were involved in its assembly and life. These rocks then took part in the building of a later supercontinents and finally in the breakup events that led to the continent's current positions. In this way, the crust produced joined and modified during Columbia's time forms part of the deep framework beneath present oceans and continents. Its internal sutures and belts still influence how modern mountain ranges form and where basins develop because contrasts in strength and thickness remain in the lithosphere over billions of years. The legacy of Columbia is also recorded in the distribution of certain mineral deposits. Many ore systems, such as some deposits of iron, copper, nickel and rare metals, are linked to specific tectonic settings, including collision belts, magmatic arcs, rifts, and large igneous provinces. Because Columbia's assembly, long life and breakup involved all of these settings, the regions that once lay within or near the supercontinent host many mineralized zones. Later tectonic events may have modified or exposed these deposits, but the original concentration of metals often reflects processes that took place during Paleoproterozoic and Mesoproterozoic times. Modern mineral exploration commonly relies on understanding which parts of a continent have Columbia age crust, and which have younger additions, because this helps predict where certain resources might be found. Another aspect of Columbia's legacy lies in the way it helps geologists understand the long-term behavior of Earth's interior and surface systems. By reconstructing Columbia and comparing it with younger supercontinents, researchers can examine how the mantle and lithosphere respond to having large continuous blocks of thick crust at the surface, how patterns of subduction and upwelling change, and how long-lived supercontinents influence climate-ocean chemistry and the evolution of life. The time interval in which Columbia exists overlaps with important steps in the oxygenation of the atmosphere and in the diversification of simple eukaryotic life. It also shows a style of tectonics in which a supercontinent can persist for several 100 million years, with relatively stable interiors and long active margins. These observations feed into broader models of how supercontinents form, how long they last, and how they eventually break apart. At the same time, Columbia's legacy includes uncertainties that remain in present research, because the rocks that record its existence are very old and have often been reworked by later events. Some aspects of its original shape, its exact boundaries, and the detailed sequence of its breakup are still debated. Paleomagnetic data, geochronology, structural geology, and geochemical studies continue to refine the positions of cratons and the timing of key events. Different reconstructions may place the same block in slightly different positions, or interpret the same belt as a suture in one model and as an active margin in another. These differences do not erase the evidence for a long-lived Proterozoic supercontinent, but they show that the picture is still being improved as new data and methods become available. In the deep crust beneath modern land and sea, the physical remains of Columbia are layered and folded within younger structures, but they can still be read by combining many kinds of evidence. Ancient collision belts, high-grade metamorphic zones, large igneous provinces, mafic dike swarms, and thick sedimentary successions all carry pieces of the story. Paleomagnetic poles and isotope systems add further constraints. When taken together, these clues show that Columbia is one of the earliest well-supported supercontinents in Earth's history, that it assembles from scattered cratons, persists as a large stable landmass for hundreds of millions of years, and then undergoes progressive internal stretching and reorganization that lead toward younger supercontinents. The continents that exist today still rest on this foundation of ancient crust. Their shapes, internal structures, and some of their resources reflect the long period when Columbia was present, the ways in which it interacted with the mantle, ocean atmosphere and biosphere, and the paths its fragments followed through later cycles of breakup and assembly.